Welcome, everyone. My name is Surmiak, and I work with Professor Udo Bach. And I would like to introduce you to the material discovery platform that we are actually building. It's a multi-million-dollar project that was sponsored by, that's actually a joint effort of a couple institutions. So our main key stakeholder is ACAP, Australian Centre for Advanced Photovoltaics, and also key stakeholders are CSIRO, Monash University, Australian Research Council, Centre of Excellence in Exciton Science, ANFF, and MCM. What's important, and what I would like to mention, that the facility that actually we're going to be installing will be installed at MCN. That's going to be our Victorian node at Monash University campus here in Clayton. So exactly inside of the MCN's clean room, we'll install our robotic beast. The system will be accessible for all the users. So I want to encourage you all to, be patient, because definitely you're going to be able to use that platform. It's not only that we're bragging about it, it's just going to be open access. It's going to work similar to Synchrotron. So you're going to book your platform time for a couple of days, and there's going to be platform engineer, that's me, who's going to help you to run your experiments. We're gonna actually, I listed here all the universities which can have access because they are part of the ACAP. And also we collaborate with NREL, which is our American CSIRO counterpart. And also we collaborate with Helmut's Zentrum in Berlin. So there should be no problems with establishing other international collaborations. We also have friends in Cambridge. And we are welcoming the entire industry. So first, I just want to zoom out from, the booking and stuff. I just want to talk you through the material discovery platform and what it is. So the major idea behind having a platform is that we've got plenty of different materials. So as you can see on that slide, I just sketched little, funnel shaped figure where you can see that you can have actually potentially millions of different combinations. And then with high throughput, you can scan through your million combinations, and then you can narrow down to your accurate, best kind of reproducible samples. And then you can have your fully refined recipe, and you can test it and confirm. And therefore, once you've got, that fully refined, perfect recipe, you're open to go to the market and, commercialize it. So we need something that's actually fast. It's combinatorial. We can scan through millions of materials, and we can produce, with high accuracy, we can produce our samples and get our measurements. So how the platform will work? So from the idea, so from your literature research, from your backgrounds, wherever you do, to EUREK, right? So first, on the left-hand side, we'll have our experiment. So all the parameters will give you pretty much all the tools that you can potentially find inside of your laboratory in one glove box. So you can, set the whole thing up, and then within 5 minutes, we'll make your sample. So we'll start from mixing and synthesis. We'll mix and we generate your ink or coating, whichever material you're going to pick. Then we're going to fabricate, characterize, and then we can store the sample, or we can access the sample, or we can, proceed with further characterization later on. It's really up to you. We will get the experiment feedback from all the data, and then using the machine learning approach, DFT, or some sort of feature extraction that we've got here, we can refine it and we can feed it back to the experiment spreadsheet and run the whole thing once again. So what sort of research, someone would ask? We are mainly focused on the solar cell materials, solar fuels, and battery research. Plus, there's whatever possibility, there's all the novel materials you can imagine and all the concepts, and it doesn't need to be related to, energy materials. It can be anything else. So, you know, just to name some, you can see on the, you know, hydrogen applications, ammonia, hydrazine, perovskites, tandem silicons, cadmium tellurides, or graphene, you know, some, you know, new kind of battery applications. Pretty much everything that you can, you know, make a coating, make a film, and therefore, you know, somehow cast it on your substrate and measure. So what's the challenge? You know, challenge is that at the moment, right, everyone is fabricating their samples. We've got a stepwise parameter change sample fabrication. So those samples on the left-hand side are mine. So I was just changing one parameter, and therefore I ended up having a huge array of samples. Or on the right-hand side, you can do combinatorial material mixing. So you can actually mix many different samples, and you can have, you know, pretty much unforeseen outcome on your substrate, right? So the question is, you know, why can't we just do that manually, and why manual research would kind of go into the past with this unique material development, material research platform? First of all, I just want to bring your attention to you know, the slide that I've got here. So this is like part of the research related to nickel oxide and perovskites. So we've got the same material that actually been deposited on the substrate in different conditions, and as you can see, if it's not mixed properly, or you know, the conditions are slightly different, you might end up with beautiful photovoltaic film that actually ready for your solar cell device, or you can end up with something that actually is pretty bad. On the other hand, you know, if you, for instance, don't control your, you know, parameters, humidity, or your plasma, or time between your plasma treatment and deposition, you also might end up with very, very bad sample, and you pretty much waste a lot of time and resources. And, you know, on top of that, there is a human error, and we have to factor that in, because no one's able to produce thousands of samples per day. It's impossible. And then what we can do, we can produce them, and we can characterize them exactly in the specific conditions, and we can track those conditions. So what are the capabilities? Yep. Okay. So first of all, this is the BEAST. So it's a 12-meter system. We've got the glove box for inks. We've got the preparation, and we also have the characterization. This is pretty much the how the layout is being divided. So on the, you know, glove box 1 and 2 will be just for the film preparation and material synthesis, and on the right-hand side we've got the film characterization. The key functionalities. So first of all, it's going to be automated synthesis. Then we've got plenty of sensors, and we can measure pretty much real-time oxygen, water, like hydrocarbons, temperature, turbidity, and we can actually add timestamp. And we'll also have the automated dosing, mixing, shaking, weighing, dripping, capping, uncapping of our vials. And, you know, we can actually move our vials without, you know, human intervention at all. Then, you know, this is the layout. So we just load the Excel spreadsheet into our robot, press one button, and basically everything magically happens. In the glove box 2, we've got some sort of functionalities that I've listed here. So we've got the handling, picking, placing, rotation, etc., etc. I won't be going into the details. If someone wants to inquire and ask me, obviously we can have time later on. But what we've got inside, we've got 6-axis productivity arm that actually will be doing exactly what your PhD student or postdoc researcher is doing. So basically we'll do spin coating, blade coating, doctor blading, you know, dripping, whatever you can imagine. We can also do electrochemistry, up to 6 flow cells, fully automated. We have 10 independent annealing stations with gas flow and solvent removal functionality. So it's a fully loaded glove box. Glove box 3, we can run UVVs, NIR, absorption, electrochemistry, fluorescence, photoconductivity, Raman, XRD, profilometry, macro photography, and turbidity. I'm just like showing you a couple of the screens that I actually sketched for like of the systems that we are building. Again, if someone wants to inquire, I can share them with more details. And you know, the last glove box pretty much is for the XRD. So it's got conveyor belt. It's very unique bespoke system actually that we will build inside. So we've got the queuing of the samples, and therefore we can run XRD and extract many other features. So what can we actually extract? So we can extract the transmissions, reflections, absorption, band gap, fluorescence. You can read pretty much everything what I listed there. But the most importantly, we can have hundreds of samples per day, and then you can actually put them into your device. You can take them out of the system. You can make your battery, fuel cell, solar cell, or transistor. It's all up to you. Any questions? Sorry, I rushed through because 10 minutes is just not enough.
Thanks, Adam. Very interesting talk, and a good example of capturing the benefit within ANFF. Last I checked on Slido, I didn't see anything, so let me just quickly double check. No, we do. Okay. So, oh, this is great. So Tatiana is asking a question I was going to ask. It's a practical question. With so many different materials and inks available, how are the dispensing tools cleaned in between types of materials to avoid cross-contamination?
So we actually have fully all the solutions. I think I can show you that slide, so it's going to be a little bit more descriptive. So you can see the whole layout. So pretty much these are all industrial kind of purging devices, which are, and also we use single-use tips. So we never really contaminate our machine. So we've got the single-use tips, and then we can purge through the box because we've got pretty much the whole range of the latest purging units. The gas purging. We've got also sensors for the hydrocarbons and other materials. So pretty much the whole Glovox one, where we do the synthesis, is fully loaded, and it makes sure that whenever we introduce new material, it's going to be pristinely clean.
Thanks, Adam. And another question from Vard. Do you combine machine learning with theoretical modeling, or machine learning, or is machine learning used to model the experimental data? I think I read that right.
Yeah, so that's actually, this is combination of both. So this is pretty much the first time in a history that you can have unique platform in the, pretty much throughout the world. We never seen the platform that actually can do both machine learning and sample fabrication, and then feed it back in and actually refine. So you can do machine learning, DFT, and you can actually just extract features. And for that purpose, we're about to, we're about to place the order for really good computers. So yeah, that's how we're going to resolve that.
Okay, from AC, when will MCN Centre, when your facilities be up and running operational?
So the order actually will be placed within this year, and the construction, so the first half of the box will come within 6 months. So as you can see, the box is divided into two. So one is sample fabrication and the other one is sample characterization. The first half of the box will receive within next 6 months. Of course, it's going to be time because we need to get used to operation of that. As I said, it's a unique system. We don't really know when we're going to set it online. However, I would say that 2020, pretty much next year would be for us just to test and set everything up. So the year after.
Great, thanks, Adam. I'm just looking around. I don't see any hands up in the room. I don't see anything else on Slido. So I think we have answered the questions from the community. Let's thank Adam again for his presentation.
Thanks so much.